Hey, welcome back. In the last video, we further discussed the convolutional layer by going over an example, where we have an image of an X in pixel representation that's processed through the convolutional layer to ultimately output three filtered images that are consistent with specific features of the image itself. The output then goes through a pooling layer. What is the pooling layer? The pooling layer acts to shrink the image stack by reducing the dimensionality of the representation of each feature map, thereby also reducing the computational complexity of the model, although it retains the most important information, such that our feature of interest is still consistent with its feature map. Pooling is done to help avoid overfitting, which will be more clear in just a bit, but in the pooling layer, we make use of a pooling operation. There are different types like sum or average, but for now we're just going to talk about max pooling. We'll make use of the max pooling operation, which reports the maximum output within a rectangular neighborhood. That is, what we'll do is specify a kernel with 2x2 dimensionality and convolve it throughout each image, such that it only takes the maximum value in each neighborhood, and it does with a stride of 2 along the spatial dimensions of the outputs, meaning whenever it processes the rectangular neighborhood of the image of the feature map obtained from the convolutional layer, it's going to shift at a step size of 2 spaces and process the next rectangular neighborhood. If we continue this entirely across the entire image for all the images, eventually we end up with the following images, with the following feature maps. Ultimately what it does is it scales down the feature map size to only account for the maximum values. But at the same time, notice our feature map is still consistent with the feature of interest. The first feature map that was scaled down still retains the feature of interest, the front slash. The second feature map scaled down still retains the X feature in the middle, and the third one scaled down also retains the feature of interest. All the other feature maps, all of them still maintain their relative pattern, and this can actually be better observed if the bright pixels in each feature map are highlighted. Which is ideal, but also begs the question, why was it scaled down? Well, the first reason being is it reduces computational costs, reduces the number of parameters in the image, and helps to reduce overfitting by providing an abstracted form of the original feature map. But even then, it still preserves the general patterns such that it's almost half the size of the original filtered image, but now our image is more manageable. Considering the destructive nature of max pooling operations, it's worthy to note that the maximum value being taken into account in each image corresponds to a region in the image most prevalent to the feature of interest. This is essential, since considering another X image, which, after being passed into the convolutional layer, suppose the maximum value corresponding to this specific subfeature of the new image occurs such that it's slanted to the left, belonging to the same neighborhood, or it could have been slanted a little to the right. Regardless, if you're looking for that specific feature in the image, the value is still going to get picked up during the pooling operation as it corresponds to the maximum value in its respective neighborhood. The same thing occurs for all other maximum values, regardless of where they would be located. Max pooling provides a scale invariant representation of the image, which is very useful as it allows to detect features in an image no matter where they are located. Pooling helps make the network remain unaffected by small translations in the input image or any distortion, because when taking the maximum value in a local neighborhood, the output of the pooling layer is still going to be very similar. This is really convenient as it helps to generalize features to more than one image. In summary, pooling helps to reduce overfitting by reducing the number of parameters and computations in the network by providing a more abstracted, generalized representation of the original feature map. Here's a nice real-world example of max pooling on a feature map that was just passed into the ReLU activation function. Alright, back to the example, applying this to all of our filtered images, to all the feature maps from the convolutional layer, outputs a stack of 3 smaller images in the pooling layer. Now, due to the destructive nature of the pooling layer, we usually keep the window size relatively small. In this case it was 2 by 2, with a small stride of 2. In the case of a much bigger kernel, a kernel that's bigger than 3, this would have significantly decreased the performance of the model. To recap all of this, the image is first processed in the convolutional layer, where the convolved images that clearly depict specific features from the image are then operated on by the ReLU activation function to produce the final output, and then scaled into an abstracted form of the original feature map, preserving the general pattern. More and more convolutional and pooling layers are added to further filter out the image. In this case, it seems that the second convolutional layer performs another convolution on the output of the first pooling layer, using 6 filters to produce even more feature maps. These feature maps further extract even more useful features from the images, where ReLU is then applied to account for nonlinearity, and once again, we apply the max pooling operation to scale down the feature map, reduce its dimensionality so as to prevent overfitting, yet still retain all of the important information, such that features are invariant to small translations, distortions, and so on. The deeper your network, the more filters build on top of each other, and thus the more complex patterns we're able to encode. But note, as we go deeper into the feature maps of this neural network, they become unrecognizable, which is perfectly reasonable, since they contain less information about the image, but more information that can help distinguish which class the input image belongs to. More information that's helpful for the computer. That is, in the beginning, we're encoding for low-level features like edges, or curvatures, or basic shapes, but as you go deeper, it starts to encode for much higher level concepts, like the cat's ear, or nose, depending on which feature detector or which filter is being convolved. In each layer, we apply kernels whose values are trained to detect a certain feature. The filters in the beginning are trained to detect very simple shapes or edges, since low-level features like edges, corners, or ridges are located in the entire image. That is why in the first layer, no matter the filter, all of them retain most of the important information in the image. But going further, since filters are being trained to encode for distinct high-level shapes, which are present in very specific parts of the image, it pretty much filters all the other information and only retains the information that's relevant to it. Once again, hence why the images seem unrecognizable towards the very end. So in summary, the lower layers correspond to simple aspects of the image, whereas higher layers correspond to increasingly sophisticated features of the image, shapes and patterns that will help the neural network identify which class the image belongs to. Here are some depictions of convolutional neural networks. This one aims to classify a car. This one here aims to classify the number 8. A much more clear example of how the pooling layer scales into an abstracted form of the original feature map that was produced from the convolutional layer. There are 2 convolutional layers and 2 pooling layers and 2 fully connected layers. Having already covered convolutional and pooling layers, their functionality should be very straightforward to you by now. It's only the fully connected layers that haven't been discussed yet, which is what will be covered in the next lesson. But again, notice that going deeper into the neural network, the more unrecognizable the feature maps become. To gain a solid understanding of this, instead of looking at the images in each convolutional layer, it is helpful to also look at the kernels. This image was obtained courtesy of Towards Data Science. Previously, you saw how filters were denoted by numerical arrays. the depth of the array corresponding to the depth of the image. The following denote visual representations of some set of filters in a convolutional layer. Looking at this, these filters belong in the first convolutional layer of some neural network. They seem like pretty simple filters. It seems like they mostly detect edges, colors, and simple shapes in some input image. By convolving each of these kernels onto whichever input image is being passed in, we would obtain feature maps. In these feature maps in the first layer, they would retain most of their information and remain relatively unchanged, since the first set of kernels only encode for very simple features, which most likely are present in the entire image. But then, the deeper the neural network gets, the filters become more and more complex, building on top of one another, and becoming increasingly sophisticated in terms of the high-level shapes that they start encoding for. The way the neural network learns to detect complex features is analogous to how humans learn. At a young age, you're taught very simple concepts, but then, building on top of previous knowledge, with practice you can start to learn and understand more complicated structures and patterns. Similar to how with training, the filters can start to encode for distinct high-level shapes that are present in very specific parts of the image, hence why the images start to seem unrecognizable towards the very end, as they contain less information about the image, but more information about that specific feature that's distinct to the kernel that was convolved on the image. Looking at this, it is apparent that filter 41, the one that I'm pointing to right now, is clearly a bird detector. Notice how there are multiple bird heads in the filter. This ensures that if the input image had some bird in it, the particular location of the bird in the image doesn't matter. If the bird is somewhere, the filter will pick it up. Simply enough, encoding the bird head in multiple locations of the filter ensures that it can detect the bird in several positions of the image. Another example of this, the more intuitive one, is face recognition. These are filters that can be used to detect someone's face. The kernels in the lower layers, once again detect simple features in the image, such as edges and bright spots, and the kernels in the higher layers start to build on top of each other and learn to encode more complex patterns. In this case, the ones in the higher layers start to identify more complex face-like features. And finally, this wouldn't be a fun tutorial if you didn't get to see this in action. What we'll do is go on a 2D visualization of a convolution neural network simulator. We're going to be coding something like this ourselves in a few videos, but if you want to access the simulator, feel free to write down the following link. It's not really that long, but essentially what they did was they loaded training images of numbers and trained a model to fit the training data. It was trained to develop filters which build upon one another with some set of weights and bias values that are used to detect specific features in the image and classify it accordingly. The deeper we go into the network, the kernels start to encode for higher level shapes. And now the neural network is able to classify newly inputted images that it hasn't seen before. So if I were to draw the number 9, its first guess is 9. Not bad. Feel free to experiment with it. Now, how does classification actually work in convolutional neural networks? The convolutional and pooling layers are used for feature extraction and data representation. Once the necessary features have been extracted, then the fully connected layers is what we use to classify the data. These will be discussed in the next lesson.